3, 2, 1, and welcome to Math 414, Summer 2022. I'm your instructor, Professor Christopher Lee, and let's get started. Let's get right into it. All right. Okay. So before we do that, about me. So I looked at the roster. Some of you know me. Other people may not, but there's me. Ooh, and this is my family. There's my wife Allison, our daughter Charlotte, and our daughter Olivia. This was back in November, so Olivia's a lot bigger. Charlotte looks kind of roughly the same. But Charlotte's going to be 5 on June 23rd, so coming up soon. Liv is going to be 1 in September 5th, close to my birthday in September. My wife's birthday already happened, and yeah, there you go. All right, so a little bit more about me. Obviously this course is online, so you're not going to like actually see me, so I want to give you a little bit about me so you get to know me, although throughout the videos I'll be going on all sorts of weird tangents, for those of you who have had me before. All right, I am originally from New York. Specifically, I'm from Long Island, and I'm from a town called West Islip, is how that is pronounced. Fabulous West Islip, New York, hometown of actor Ken Marino, if you know who that is. My neighbor went to high school with him, so that's about that. There's some other like random people that are from West Islip. Mike Komisarek, who's a hockey player. There's somebody else too. There's like a weird one. That's Chris Angel, the magician. Allegedly lives in West Islip, although I literally never saw him, but whatever. Anyway, so originally from New York. So speaking of New York, I went to school in New York. I went to a school called Clarkson University, which is in a town called Potsdam, New York, not Potsdam, Germany, Potsdam, New York, which is up by the Canadian border, which is where I met my wife. She's from that area. At that school, I acquired 3 degrees. I'm one of those people that got all my degrees from the same school. I got my bachelor's, my master's, and my PhD in mathematics. And specifically, I did my research in analysis, so I am very excited. And in fact, I haven't taught this course since 2016, which was before I had kids. So I'm very excited to be teaching 414 once more, because analysis is my life. It is, when I first took this course, it gripped me like no other math course did, and I haven't looked back. But speaking of looking back, though, in addition to an analysis taking up all of my free time, of course having an exciting family, the other thing that I've been spending a lot of my time on is chess. I was actually in chess club back in the day, but the teacher who ran the chess club I did not like at all, so I just stopped going. But when the pandemic hit, I got back into it. Check it out. I got a name, a math name. Ooh, Bishop's Lemma. So I was actually very shocked that this was not taken on the bad chess website and the good one. I haven't set up an account on Chess24 yet, because why would I? There's like some other one, like Kasparov Chess. There's a couple of other ones floating around out there. But anyway, so actually in my research, I actually used something called Bishop's Lemma after a mathematician named Eric Bishop. That's my handle on both websites. For those of you interested, I mostly play rapid games, and my rating on chess.com was in the 1600s, but as of this recording, I've plummeted horribly back to the 1400s. So, oh boy, I'm 1900 in Lee chess though, so let's leave it there for a bit. All right, and like I said, I'm gonna of course divulge more gross facts about myself as we go on. So let's talk a bit more about what this course is all about. Okay, so in your calculus courses, so here at Iowa State, 165, 166, 265, our focus is on how to use what's true. Right, spent a lot of time going like, hey, derivatives are this, and here's what you do with them. Integrals are this, and here's what you do with them. And even in differential equations and some of your other math courses, a lot of them are more a bit focused on, all right, let's use some stuff to solve problems. But this course, and its sequel, 415, which I recommend you take, it's a fun time, we're going to focus our attention rather on how is this stuff used. Right, so a lot of our focus will not be on, hey, do this derivative, or hey, do this integral. Our focus will be more on, okay, well, why is that stuff the way it is? And, of course, the dreaded question in any math class, do we really need to care? And the answer is yes. Hopefully you believe the answer is yes, maybe you don't. The answer is yes, because even if you know how to use things, you will run afoul of stuff that you don't, right? If all you have is a hammer, right, you think everything's a nail. You need to have more tools in your toolbox. So, for example here, for sake of argument, if I ask you to compute this, right, if I ask you, here's a pause the video moment, you hopefully can do this, although I do know when you get a little further in your math courses, like, you totally forget how to do shit like this. But, right, this is not bad, because, oh, alright, I integrate this, x cubed, evaluate at 1, evaluate at 0, take the difference, it's 1, right, I picked one so it would come out very nicely. Right, so like in calculus, right, we drill how to do this sort of stuff. Right. But the reason this all works out so beautifully and so nicely is that this function inside here is particularly nice. Right, and there's a reason that its definite integral, right, is solved in this manner. All right, there is a fundamental theorem that you may or may not remember. Now, let's say I change the deal and said compute this, where now my integral, my function now, is not a nice polynomial. Instead, it's this monstrosity right here. So you give me an input x, and I find out the smallest n, so that x is a less than 1 over 10 to the n. So, for example, if I plugged in 1/2, the smallest n would be 0. Right, because 1 over 10 is less than 1/2, not bigger than it. Okay, and so for example, we can plug in some other values. One thing you might note right away, of course, if you're a little bit of a laser eye, you'll go, well, wait a minute, if I plug in 0 here, then there is no minimum. So this is technically an improper integral if you're really going to be focused on it. But note, right, you can't just do this to actually compute this integral. Right, it's not enough to go, oh, well, I'll just integrate this. I would love for you to give me the antiderivative of this. I'd be very impressed if... now that I pause and think about it, I think it actually probably doesn't have that awful of an antiderivative, but it's not going to be anything as nice as this. And then computing its integral, good luck just plugging in the endpoints. And again, right, it's improper, so you really can't do that. Right, so that's not easy at all to do. Right, this is a significantly more complicated function than a nice polynomial. And by the way, if you are interested, the value here is 1/9. So take a moment and figure that out, I guess. Okay, and you might look at this and go, all right, sure, buddy, fine, I get it. This is a reasonable function, and there's some theorems that we can apply, right? There's some theorems you're taking for granted and not thinking about because... right, most functions we work with are nice, but you might go, oh, this is just some contrived nonsense you came up with. Well, why is analysis even a thing in the first place, right? I could argue this, all day long of like, well, you really need to know how integrals work because, like, there are functions that there's just you can't do this. You gotta get creative. You gotta go to the definition and really work with it. Right, so I could say that all I want. Now, historically, there was a reason analysis came about, and it was during the 1800s, and if you want somebody to blame, it's good old Fourier. So, in the 1800s, Fourier decided to study heat propagating through a solid body. Specifically, he was looking at a infinitely long piece of metal, because, sure, and he wanted to know if you applied heat on the bottom, what's the heat going to do as it travels along the infinitely long piece of metal, right? He was interested in, like, as heat propagates, what does it do in the long run, right? It doesn't just disappear, what does it do, right? Like, obviously it gets arbitrarily small, but he wanted to really understand that. And so he cooked up the following thing, right? And so now the function I showed you before, that minimum of 1 over 10 to the nth thing, right, you might go, that's contrived. Who would come up with something like that? Well, look at this nonsense Fourier cooked up while studying heat, right? Like, this is really, like, if you think about this expression, there's a lot going on here. Of course, there's a 4 pi out in front, because what he really figured out was that this is equal to pi over 4. But what he's doing, he's summing up cosine infinitely many times, and he's got coefficients flying around, and the coefficient inside on cosine is involved with the indexing as well. Right, this has got a lot going on with it. Right, and he cooked this up while he was studying heat, while he was studying a physical problem. Right, so a significantly complicated expression can show up from physical phenomena. And when Fourier presented this, not everybody agreed. So, Fourier is a name that you may have ran into before, maybe not. Lagrange, though, was definitely somebody you ran into because you did Lagrange multipliers in Calc 3, and I bet you loved them. So this is what he looks like if you want to hate on him. So when Lagrange saw this, and I don't know how he sees this, Lagrange sees this and allegedly is like almost immediately like, yeah, no, that's bull, dude, that's not true. And then Lagrange specifically points out that if you take the derivative of this, and note what he does, the left-hand side needs to be 0, right? No, this is good for all x between -1 and 1. And what does he do to compute the derivative here? He does it term by term. He says, oh, let me just take the derivative of this, and it cleans up like this. Note that this would pop out, and a 2 would pop out and get rid of that, and a pi gets taken out. Right, so actually computing the derivative here isn't too bad. But Lagrange notes that if you plug in 1/2 into this thing, the summation turns into the following. It's 1 over root 2 minus 1 over root 2 plus negative 1 over root 2 minus negative 1 over root 2, and then the terms just repeat from there. So Lagrange points out, quite correctly, that something is amiss, something is not right here, because if this is true, if this holds, your claim, Fourier, then I know for sure that this expression has to equal 0, and expressions of this form, where you've got alternating terms and you're adding them up infinitely many times, and note that they all cancel each other, mathematicians of the time knew that that kind of a summation was problematic and did not have an answer, right? You couldn't definitively say it was 0. So Lagrange goes, there's got to be something wrong, because there's no way this is true. Right, and what's going on here, quite surprisingly, and we'll slowly work our way to answering questions like this, Lagrange is actually wrong here. Which is interesting, because if you kind of look at this and go, well, if I took the derivative, it's like, that's what the derivative should equal. It turns out that Fourier is right, this is true, and Lagrange is wrong, because it turns out you can't actually take the derivative of this in the way that he wants you to. The term-by-term derivative of this does not work. Because, again, Lagrange is forgetting, right? And Lagrange is just using what he knows. He's not thinking about why that stuff works in the first place. He's just using, oh, if I hit this with a derivative, I'm going to get some bullshit. But he can't hit it with a derivative. You're not allowed to take the derivative of this. Because this is not a summation, you can't do it term by term. This is a limit. So there's a fundamental piece of information here Lagrange is completely overlooking in his argument. And this kicks off throughout the entire 1800s, as we will go on for the course. I'll bring up this time period in mathematics a lot, because a lot of what we're talking about was figured out in the 1800s, which, if you're thinking about the history of mathematics, is pretty recent. So, what was happening, and this really kick-started the argument off, where people really started getting into it, you can't just know how to use stuff and apply it all the time. You have to know why it works, because you cannot just use it willy-nilly. You need to know when and why and how you can use it. So there is a very good reason why this course even exists in the first place. Alright, so, that being said, well, where do we begin? Alright. Okay, we're going to move a little fast here, because most of what I'm going to talk about right now is stuff that you saw in your proofs course, but this will mostly just serve as a review, and also serve to set up notations and my own mathematical neuroses that I've got. So where do we begin? Right, so if we're going to rigorously study calculus, we should have a firm foundation that we plant everything on, and the modern building block in mathematics is the idea of set. The notion of set. And sets are just collections. That's it, but they've got some technicalities, and they got some subtleties, and you gotta be a little careful about how you work with them. So specifically, a set is a collection of objects. The objects inside of sets are also sets. So, in other words, everything in math is a set. And the key property is that the two things you would want to talk about with a collection, whether you belong to a collection, and if I have two collections, when are they equal, those have to be propositions, meaning that they're true or they're false, and that's it. They can't be simultaneously true and false, and they cannot lack a truth value. They have one from a choice of true or false. There's no third or fourth option. Okay. And when we talk about sets, we denote them using all sorts of symbols of various sizes and gaudier fonts. Sometimes we go over to other alphabets and steal some letters. But that's the deal. The membership proposition, the statement that a set belongs to another one, we write in this beautiful way here. X is a element of A, or it's a point of A, or it's a member of A, or it's in A, however you want to say it. And when that doesn't happen, we put a slash for it. Quick side note, again, talking about old-timey mathematics, back in the day, this was just an epsilon. People just used epsilon for this, but then epsilon started getting used for other purposes, so, more on that, of course, later in the course. So if you do go look at, like, an older math textbook, you will find epsilons instead of this symbol. Alright. Okay, and equality is denoted as usual, A is equal to B. And when A is not equal to B, you put a, hey, I just copied and pasted, look at me, ooh. Ooh, boy. Watch out, lazy over here. Let me fix that. Okay, where is it? Okay, study. Hey, there you go, and it is. They not equal to B, alright. Cool. No matter how many times I go through these slides, no matter how many times I read and reread and practice, there's always something wrong. Oh, no matter what. Anyway, alright, it should be fixing itself in a moment here. Oh god, why is it taking so long? Okay, there it is. Whee! Okay, yeah, my computer is not plugged in. I thought that happened. Why is it not working? Why is it not charging here? Alright. Oh, there we go. Okay, now it's working. My screen did that weird, like, the color changed for a brief second. I was like, whoa, what's going on? That's because, yeah, my computer wasn't plugged in. Alright, anyway. Okay, let's back to it. Okay. Hooray. Okay, let's keep going. Alright. So, sets are equal precisely when they have the same elements. So, in other words, A is equal to B when X is in A and X is in B are equivalent for all sets X. Right, and that makes a lot of sense, right? If I have two collections and I say they're the same, their contents must be the same. That's not a huge stretch to convince yourself of this, but it is worth noting that when I make this claim here, right, all I've said about sets is that, oh, you know, you have membership and you've got equality, and, you know, that's it. And what I'm doing now is, what I'm really doing here is setting up an axiom. I am asserting that this is a property sets have, right? Because if you just start with the idea of a set as just a collection and that's it, well, then that's meaningless. It doesn't have any girth to it, you know, it doesn't have any meaning to it. So when you start asserting stuff like this, what I'm really if we're getting into, like, formally how you set this stuff up, I'm really asserting some axioms here, right? And again, these are just here to clarify what sets really are, like how they're supposed to behave. They're collections, but they're mathematical collections ultimately, so they have to have some rules to them, and here's one of them. We will see a few of these as we go forward here. All right, and normally when you prove two sets are equal, very rarely do you invoke this particular fact that, oh, being an A and being an and B are equivalent statements. Rather, what you do is prove subset in both directions. So recall that a set is a subset of another one if every element of A is an element of B. We write that with this fancy symbol here. Side note on subset symbols. That's the symbol I use for subset. Some people use, and again, why is it taking so? Okay, some people use this for subset. They put the little line under it. I hate that. I hate that so much. I don't like that at all. There's a very good reason why, and when we talk about ordered sets in the next video, you can use subset to order things, so people want this to be like a less than or equal to, so they put a line under it. I never did it. I was never even taught that. I was always shown subset like this. And in LaTeX, to create the symbol, it's just /subset. And, yeah, so, and honestly, in my own research and the papers that I've read, everyone uses this. Like, nobody uses the subset with a line under it. That's how I do it. I know some people are very particular about their subsets, but that's how I write it. Okay, so note then that A is equal to B precisely if A is a subset of B and B is a subset of A, because note this is just encoding this statement right here, right? Because A is a subset of B means that if your X is in A, then X is in B, and B is a subset of A means that if X is in B, then X is in A, so X in A and X in B are equivalent statements. All right. Okay, so when A is a subset of B and A is not equal to B, then we say A is a proper subset. This is just language to keep in mind. And again, we're not going to get too hung up on a lot of this stuff here. Again, most of this is here to just serve as a review and, again, set up notation and how I work with sets. So, something about sets is that we need to assert they exist, right? Because, again, I can talk about, oh, collections that have this membership and equality thing. All right, well, what's an example of one? So you gotta begin, again, asserting stuff. You have to come in with axioms and go, all right, here are things that we're allowed to do. And the classic set, which is an interesting one and has some weird properties, is the set that doesn't have anything in it. And we call that the empty set. So it's the set so that nothing's in it. And if you have stuff in it, so if you're not the empty set, then we say that you're not empty. Okay, so let's actually do a proof now, and again, this is to just sort of set up and get a feel for how I like to write proofs and how I like to do things. So I'm going to call everything a proposition in this course. Some books will, like, do, like, lemmas and theorems and corollaries and other things like that. Everything's a proposition, whatever. The designation, the difference between theorem, lemma, is immaterial. So I'm just going to call everything a proposition. So a statement that possesses a truth value, and in particular, all of our propositions will be true, and will come with proofs completely convincing you of their validity. So, alright, so what we're going to prove here is that the empty set is unique in its key property. So any set that has this property here, that nothing is an element of it, must be the empty set. So not only does the set exist, but it's the only set with this property. Every other set must have stuff in it. Which is good, because it'd be weird if there were multiple sets that just didn't have anything in them. So, alright, okay, so let's say that they were not equal. Now, so remember, this is a proposition. If you're equal or not, right? So either you are the empty set or you're not. Now, if you're not the empty set, that means that one of the subsets needs to fail. Either A is not a subset of the empty set, or the empty set is not a subset of A. Okay. Alright, now in the former case, that would mean that there's something in A that's not in the empty set. But, right, by the assumption of A, nothing could be in there. So it can't be that A is not a subset of the empty set, and, right, in the latter case, well, if the empty set wasn't a subset of A, that means there's something in A in the empty set that's not in A. But the empty set doesn't have anything in it, so you get the same contradiction. So it's got to be that these two sets are equal. If they're only equal, then there's an element that lives in one of them, but there can't be anything in either of them, because that's what the empty set is. That's what we assumed A had as well. There we go. Beautiful. Alright, not a bad proof. Also a proof that, again, highlights a thematic thing that happens, especially early on in this course, which is that we're going to prove a lot of stuff that's very, like, obvious, and the proofs are not, like, the most enlightening thing ever, because a lot of these proofs are really just an exercise in pedantic tree, if that's a word, pedanticness? Pedantic in nature. Yeah, I'm not quite sure the right way of saying that, but a lot of the proofs here early on are going to be just sort of like, yeah, like, we're setting stuff up, and we're, right, because they're building a foundation that we're going to put everything on top of, and we want it to be as rock solid as we can make it, because, again, we don't want to be like Lagrange, and, you know, in 200 years everybody makes fun of us for not understanding that you can't take the derivative. Come on. Right, so yeah, you don't want people being like, oh, excuse me, that's not what the empty set is? Yeah. Alright, cool. Alright, so let's keep talking about sets. Alright, so sets can be created using something called set builder notation, and broadly this is written with curly braces on the left and right. I put a colon between them. Some people put a bar. I like the colon instead of the bars, so that's what I use. And the notation basically says, on the left you've got sets, and on the right you've got something that they satisfy. So over here on the left of the colon is the sets that we're interested in, and on the right the things that they belong to. So again, here it's understood that if you're an element of this set, then you are a set satisfying whatever this proposition is claiming. Alright, so set builder notation is great, but it's also probably one of the worst things that ever happened to set theory. And let's talk about that. So, there are some ins, some outs, and what have yous about set builder notation. So, the things that are on the left of the colon have to belong to some previously established set. And in the notation, you see that sometimes as X is an element of A, and on the right you've got some proposition regarding the sets. You have to do this. There has to be a set everything belongs to. And we'll talk about that in a brief moment here. Okay. Something else that we will abuse frequently is that if you create two sets using set builder notation, and you've used equivalent propositions on the rights, then the sets that you make have to be equal, right? Because if the propositions are the same, then, yeah, the sets you're getting will always be the same. So, for example, this set over here and this set over here are the same thing. Right, because equality, it doesn't matter the order in which I write an equality. If X is equal to the empty set, then the empty set's equal to X. It's just how equality works. Alright, and one last thing to note, something I will do a lot is temporarily create a set using set builder notation. So we'll do things like let A equal some set with some absurd property, like that one. By the way, think of a set that belongs to itself. Email me if you come up with one, because good luck. Spoilers, they don't exist. Well, I need to be a little bit careful with that. In the usual math universe, they don't exist. You can create them in, like, new foundations or whatever, but that's nonsense. Anyway, alright. So, set builder notation, like I said, is an incredibly powerful tool, and lets us get away with a lot of great mathematics. It historically caused a huge problem for set theory, though, and and that's all due to a mathematician you may have heard of, Bertrand Russell. The result that's called Russell's paradox, which you saw in your proofs course, the way I always like to think of it is as more of a theorem rather than a paradox, because it's not really a paradox. What Russell came up with. What Russell really came up with is the following theorem. If I have a set, then I can always find another set that's not an element of it. And why that's incongruous is, note, that implies that there's no set that contains every set. So the collection of sets cannot be a set. Even though that seems like that should be a set, right? You're either a set or you're not, right? Well, it turns out you can't do that, and one way to think of this, or one way that I had this explained that I liked, is, right, we are in the universe, we could talk about things in the universe, but the universe itself isn't in itself, right? We're in the medium of the universe, right? So sets exist in, like, the medium of all sets, but all sets themselves is not a set itself, right? They're not in there. So, there you go. So, Russell points out that, well, if you're going to allow set builder notation, which you really need to, you do have to concede that all sets does not form a set. Even though it seems like that should be true, turns out it's not. But it's not the worst thing ever. So, and of course, what did Russell cook up? Russell went, oh, hey, do set builder notation, and on the right put X is not an element of X. Okay? Because if B is an element of A, there's a bit of a problem. So B is an element of A, which means that it's subject to this. And if you start asking the question of where B lives, well, if B is in B, since it's in A, it satisfies this property, it must satisfy this property, but, right, that gives you the contradictory B is not in B, right? That can't be. You're either in or you're out. You can't be both. Alright? And if B is not in B, well, since B is in A, and it's not an element here, it means that it can't satisfy this condition, which means that you have to have B as in B. But that goes contradictory to what we already assumed. So it's got to be that B can't be in A. So note the subtlety here. In this first point, if B is in B, then you arrive at this. That does actually use the fact that B is in A. Right? Because if you're in B, you satisfy this condition here, which gives you the contradiction. The in A part comes in here, because if B is not in B, well, since we're a member of A, and B means that the set B is defined to be the things with this property, so we're in A, and if you don't have this property, well, then you need to be in the set B. That's how B is defined. So, that is the subtle point here. So like I said early on, when we're setting up sets and talking about them, we do need to be subtle about it, right? There are these little things that we need to be careful of. Alright, so there you go. What are some other things that you can do with sets? Alright, well, using set builder notation, you can make things that we will frequently use, although, again, we're not going to be so heavy on how sets work. So, union, intersection, set difference, these are the sets with these logical properties. The only thing to remind yourself about OR in mathematics is that OR is inclusive, meaning that you can be in the set if you're in both A and B. So the union is just supposed to be like gluing the sets together. So you could be in both. Right there, overlap in the Venn diagram. Alright. And you can now start establishing all sorts of formulas involving unions, intersections, and set differences. These are the three main set operations we're going to work with. There are others. You could talk about like symmetric difference and absolute complement and other things like that, which we're not going to get, again, too crazy about it. But let's, again, review, get used to how things are going to move in this course when it comes to sets. How I like to talk about sets too, so you're used to that. Alright. Okay, so let's quickly just rattle off a couple of theorems here involving union, intersection, and set difference. You'll do one for your homework to wet your whistle. Alright, so the union of A is A. Alright, well, if you're in the union, then you're either in A or you're in A, which means you're in A. Yay. And likewise, if you're in A, then... Right, you're in A or you're in A, so you're in the union. Ooh, right, like I said, pedantic. Alright, not the most exciting proof, not the most engaging, but proofs that need to be done nonetheless. We'll see a few more of those as we go on in the course. We'll get some juicy details later on. But... Alright, so let's now look at A intersect the empty set. Okay, well, if you're in there, then you're in A and you're in the empty set, but you can't be in the empty set. So it's got to be that this set right here is empty itself. Right? If X was in this set, we have a contradiction, so there can't be anything in there. So it has to be the empty set, because again, the empty set is the unique set with that property. Hey, good thing I proved that. That made this proof a little bit easier. Alright, point 3, so recall point 3 was A minus A is the empty set. Same sort of argument happens there. If you're in A minus A, then you're in A and you're not in A, which, yeah. So there can't be anything in the set. Alright, so let's now prove, what am I proving in here, that every set can be written as a union of its intersection and a set difference, and now note, B can be any set here, it doesn't have to have anything to do with A. Okay, so if you're in A, then two possibilities, you're in B, which means you're in the intersection, or you're not in B, which means you're in this set. So you're in that union. Okay. Similarly, if you're in the union, well, then you're in one of them, and regardless of which one you landed in, you're in A. So X has to be in A, so we have got subset in both directions, so we've got equality. Cool. Good stuff. Alright. Oh, therefore we must have X and A. I should have realized the block. The Helmos grave wasn't there. Alright. Okay, so another construction that we will use is this idea of listing, where, right, I can talk about a set consisting of a single element, which, again, is this, and this is the set that you write it as. And you could do this for any number of sets. You could talk about all the things in two sets, or all of the things that equal a pair of sets, or a triple, so on and so forth. One thing that's worth proving is that this set construction allows us to encode membership as subset. This is kind of a neat little property. I always thought this was cool. And I actually asked a logician once if there was a way to reformulate set theory where instead of taking membership as your like fundamental thing, was there a way to make it subset? Because right, subset you can turn into membership like this, and their answer was, there might be a way, but why would you do that? But anyway, so if anybody wants to waste their time trying to figure out that, there you go. Alright, so this is pretty easy to prove again, because so if X is an A, we need to prove that this is a subset of A. Well, what does it mean to be in that set? Well, you're in that set if you're equal to X. So if Y is equal to X, well, X is in A, so that means Y has to be in A. So anything that's in this set is in A, so we have subset. And the converse basically goes the exact same way. Right, if this set is a subset of A, then, right, X has to be in A. Because X is in this set here on the left. Alright. Okay, another set construction that is worth talking about, that we will occasionally run afoul of, is the power set. Now, so it's worth noting, everything I've been doing here, when I say these are a valid construction, what I'm asserting is that again, in order to properly use set builder notation, there has to be a set that these things already belong to. So, like, what the axiom is formally stating is that there is a set that contains all elements that are subsets of A. And then you use set builder notation to create that specific set. The power set, of all of the axioms that govern set theory, this is the one that really is the problematic one in a way. So later on in the course we'll talk about something called the axiom of choice, which that's the one that mathematicians got into a huge fight about. But it turns out that this one, while this might seem pretty like innocent, this one might be biting off a little bit more than he can chew. It turns out. Anyway, all right. So let's point out some things about the power set. So again, this is something we will just run afoul of, and it'd be good to have the notation set up here. So the power set, first of all, is always non-empty. It always has two elements in it. It always has the empty set, and it always has the set itself. And something else that's worth pointing out, that every element that lives in A, then the set consisting of it belongs to the power set. So, given a set A, its power set always has stuff in it, which is nice. Alright. So, one thing that's worth noting is that the empty set is a subset of everything, which is quite interesting. So it's a statement that vacuously holds. So there's a couple of theorems in math, there's a couple of statements that are just automatically true from a logical standpoint. Right, because what does it mean to be a subset? It means that every element in here belongs in here. Well, there are no elements that belong in here, so yeah, you can conclude that they all belong in A. Because there are none. So, from a false hypothesis, you can make whatever conclusion you want. In the words of Russell Bertrand there. Alright. Okay, and similarly, A is just always a subset of itself. Everything that's in A is in A, so there you go. Alright, and as we just proved, if you're an element of A, then the set consisting of X is a subset of A, which would mean that this has to be an element of the power set. So note the differences here of the symbol notation, so keep track of that. Alright, cool. Let's keep going. Alright, almost done, because we really only have one more thing from set theory to really talk about, and it's a big one. So, given sets A and B, then the set consisting of A and B, and the set consisting of B and A are the same thing, because they were created using set builder notation, and these are the same proposition, so they must be the same set. So, that's a little annoying at first, because you're right, when I look at these, you go, well, no, those can't be equal, because the order of them is different. But the way sets are designed, sets on their own don't care about order, right? They don't care that you put A first. Sets only care about what's inside. Very nice of them. Very beautiful. So to indicate order as well as membership, we use something called ordered lists. So when I write this, and this is a symbol that gets overloaded big time in mathematics, because in the course we will have open intervals. So, you know. But, right, when we write this, and we're clear about it as an ordered pair, we mean that this is something that consists of the elements A and B, but their ordering matters, meaning that if this does line up with something of the same type, then A and C and B and D need to be equal. Now, if you want to know a little bit of your deep lore mathematics here, everything in math is a set, so this needs to be a set, so there needs to be like a set description of it. It can be created in multiple ways. So it turns out that there's actually no canonical way of making an ordered list. This is the formulation that's mostly used in like hardcore set theory. I believe Kurtakowski is the one who came up with this, if I remember right. But it's worth noting that there is no universally agreed, like, this is what an ordered list is. There's multiple ways of creating something that has this key property. This is one set way of doing it, so if you want to, like, actually work at the details of the proof, it's, if you think some of the proofs we've done so far are pedantic, yeah. Alright. Okay. So, something that we will assert as a valid construction is the following, the set of all ordered pairs. This is called the Cartesian Product, and it's denoted by A cross B. So it is worth noting that these things all actually live in a set, because if you take their definition to be this, this belongs to the power set of a union of some stuff. There's a way of doing it if you're... Again, if you're really interested in that, but we don't need to go that far off the deep end. Okay. Alright, so now that we've got ordered pairs and Cartesian products set up, we can now talk about the last set theoretic thing that we're going to use a lot, which is the notion of function. So, recall a function is a subset of a Cartesian product with the property that if you, what's going on? Okay, for every element A, there is a unique element in B, so that the ordered pair AB is in F. So for every A, I can find AB, and in fact, I can find only one B, so that this is an element of F. Right, so in other words, a function is just a collection of ordered pairs, very specifically with the property that if you've got a input, an element from A, hanging out over here, there's only one output that could be associated with it. Now, it's possible the outputs repeat, it's possible different inputs of the same output, but if I have an input, then, by the vertical line test, there's only one thing you go to. Alright, so let's talk a little bit more about functions and how we'll announce them and notations that I use and opinions that I have about functions. So let's make some points of order. Alright, so when you're announcing a function, this is pretty universal. Everybody says, you know, A, you've got a function from A to B, and you write it like that. Alright, so the set on the left is called the domain of the function, and the set on the right is called the co-domain. Note, I did not say range. I said co-domain. Range is different. We'll talk about that in a moment. Alright, so, given a function and an element in A, the unique element B, so that AB is in F, is relabeled as F of A. Right, B is unique, so we can give it a unique symbol, and the symbol we give is F of A. So, right, you can create a function by talking about a formula for each input. Now, sometimes those formulas are incredibly complicated or straight up don't exist. Right, you can have a function, you've got a collection of ordered pairs, right, but maybe you don't have a way of explicitly describing what each output looks like. That is a thing that's possible. Alright. Okay. So we may announce a function with a proprietary symbol, and to do that, we sometimes write stuff like this, where we put a dot to indicate where input goes. So if I make a function like the sharp function here, we're announcing that I'm going to use this special notation rather than the traditional F of A. Instead, I'll do, like, you know, and we'll see later on when we talk about, like, square roots or something. Right? It's a special notation for a function. Or squaring or something like that. Alright. So let's quickly prove a couple of things about functions so we get a feel for how they work. And again, they are sets, so they've got set things to them, and so this is just a good review and good practice of how to work with them. Alright, so a ordered pair lands inside of a function precisely when the thing on the right is F of A. The only things in a function are the ordered pairs of that form. So this is also saying that a function is equal to its graph. So a graph of a function is, right, the collection of these points here. So this is saying that a function is its graph. Alright, and then lastly, two functions are equal precisely when their outputs are equal. And note something right there. So we'll talk a little bit more about that in a moment, but let's quickly run through these proofs. Alright, so if f of a is in B, then since this is... Alright, so I'm trying to prove that B is equal to f of a. How about I remember what I'm doing here? As f of a is the unique element in B with that property, it's got to be that B is equal to f of a. Surprise. Alright, again, not the most exciting proof, but a good one to see, and a good one, again, to, again, get used to all this stuff and remind ourselves of how all this stuff works. Alright, let's keep going. Alright, so let x be a set. Okay, so I'm trying to prove that if you're in F, that happens precisely if you are an ordered pair of that form. Alright, well, if you're in F, that means you're in A cross B, which means that x is equal to AB. There you go. I think I saw that typo, and I was like, oh, I gotta fix that, and then I never fixed it. I got my cat attacking me while I'm doing this now. Anyway. It's loading, give it a second. Alright, there we go. Okay. Okay, so, F is a subset of A cross B. So X landed in F, which means it lands in here, which means it's equal to that, for some A and B. Point when 1 then guarantees that B is equal to F of A. And so, there we go. X must be an ordered pair of that form. And, went too far. And then the converse is very straightforward, because if you're equal to this sort of ordered pair, then you land an F, and that's it. Cat, what are you doing? Quit it, cat. I'm almost done. Alright. Okay. And now finally, two functions are equal, precisely when their outputs are equal. So let's see that in action. Take an element that lives in A. Alright, well, as we just demonstrated, these things live in A, but if that lives in G, then it's got to equal, right, an ordered pair involving an input and an output. But if two ordered pairs are equal, it's got to be that A is equal to B, and F of A is equal to G of B, which gives me F of A is equal to G of A for all A. Okay, sweet. Now, similarly, let's say I know that the outputs line up for all inputs. Given an element of F, then it is an ordered pair of this form. Our assumption then guarantees that X is equal to this ordered pair, which lives in the set G. So that means that we have a musta that... Oh my god. How many, my fingers moving too fast for my brain typos we're gonna have here. There. Then we must have that F is a subset of G, and the reverse subset is proven similarly. So we have subset of both directions, so we have equality. Alright, so note a subtlety about that particular theorem. Two functions are equal precisely if their outputs are equal. Note that the codomains here are completely different. That's because, and this is something we're going to make use of, and it's worth talking about, because this is actually a weird point of contention to some mathematicians. I am of the opinion that you can always change the codomain of a function. So if I have a function and I have a set that contains all the outputs, then I can just have f be a function from A to C. Some people don't like this. Some people disagree with this. And those people are completely and utterly wrong, because, right, the function is just a collection of ordered pairs. Doesn't matter where the outputs live, you can change that. The inputs, of course, right, you need the domain, the beta domain, but where the outputs live, it doesn't matter. And, right, we do this all the time, even in calculus. Right, when I talk about the function x squared, that's a real valued function, but if I want to be a little bit more precise, it only spits out non-negative real numbers. Right, and similarly, something like e to the x, that's a real valued function, but it only spits out... There's the power cord again, is being silly. Yep, there we go. Okay. E to the x is a real valued function, but only spits out positive numbers, strictly positive numbers. All right. And so again, this is just running through the basic definition of functions as a set. They are a collection of ordered pairs. So if you are a function from A to B, you have your ordered pairs, and now our hypothesis gives it the f of a's live in C, so all of these ordered pairs are in A cross C. God, Olive, what are you doing? My cat is... I have no idea what you're doing, but you're not making things easy right now. And thus, f is a subset of that Cartesian product, right? Because all these ordered pairs live there. All right, and then now you just need to verify that it is a function from A to C. So you just need to verify that for every element in A, there's a unique thing in C. Well, it's a function from A to B, so there's a unique thing in B. But by hypothesis, f lives in A, but as we just demonstrated, f lives in A cross C, so those unique B's live in C. So the only thing you need to verify now is that if there is something in C, so that AC is in F, then C needs to equal B, but as f is also a function from A to B, it lives in that Cartesian product, so C is in B, and B is uniquely having that property, so B is the unique element in C, so that A is in AY is in F, which ensures that F is a function from A to C. Alright. Beautiful. So we'll talk a little bit later on here why some mathematicians are very against this maneuver here. I'm not one of them, and in fact, we are going to use it to great effect in a little bit later on in the week here in a later video. Alright, so we got a few more things about functions to talk about before we call it a day. So the first one is image. The outputs always live in a set Y, so I'm allowed to do this set construction without issue. This is called the image of the set A under F. Note A is a subset of X. And in particular, the set Fx is called the range. So when we talk about the range of a function, you really mean this set right here. Note, this range lives in the codomain, as we will point out, but it's not necessarily equal to it. And in fact, you can change a function's codomain to be anything, any set that contains its range. Alright, and there are all sorts of properties that you can prove about images. Like I said when we were talking about union and intersection of that, we're not going to do like a full exhaustive list of everything you could do with them. That'd be ridiculous. But it's worth giving us sampling, giving us, again, a taste, a reminder of how all this fun stuff works. Alright, so for example, f of a is in Y, that holds for any A, so the image has to be contained in Y, right, because Y is a codomain for the function, so all of its outputs live there. Similarly, if you are in X, then your output is in the range, and that was a subset of D by hypothesis, so you can change the codomain to be D, because all the outputs live in D. Alright, now let's prove that the image of A intersect B is contained in the intersection of the images of F, of A under F and B under F. Alright, so if you're in there, then Y is equal to f of X for some X that lives in the intersection. That implies that X is in A, so f of X lives in f of A, so again, remember that's what this set is, it's the collection of outputs. And similarly, if X has to be in B, and thus f of X is in FB. So you're in both, so it means you're in the intersection. Whee! Okay. Not bad at all. Alright, let's keep it going. So, one way you can announce functions is using something called indexing notation. So I can tell you a function by writing something like this. where it's understood that I have a function whose domain is lambda here. Again, codomain does not matter. You can change it to be whatever you want. But I have some method of associating a unique element to each element in lambda. And that this set here specifically is the range. So equipped with this, you can talk about an indexed union as follows. So there will be times where we want to union things, but we want to union up more than one set. So we use this construction here. And as long as the indexing set is non-empty, you can then talk about an indexed intersection. Note, if you allow an empty set here, then this proposition, right, that's vacuously satisfied for every x. So over here on the right, you'd have every possible set. And we know that that's not a set, so yeah, can't do that. Alright, so let's do a quick little proof involving index unions and index intersections so we get a feel for them. And again, we will occasionally use these throughout the course. Again, this whole first video is really, hopefully, just a review of some things that you already know, and again, establishing notations and the ways I like to do things. Alright, so this is a result saying that if I take a set and delete a union, that's the same thing as doing the intersection of that set getting deleted by all the indexed elements. So it's worth doing also, if you've, for the eagle eye amongst us, this is one of De Morgan's laws. Right, so let's work through the details of the proof here. Alright, so if you live in this set, that means you're in A and you're not in the union. Alright, well, if you're not in the union, that means you can't be in any one of those elements. Right, because if you're in the union, that means there is some index that you belong to. So if you're not in the union, then you're not in any of them. So that means you have to be in this set for all lambda, which means that you're in that intersection. Okay, and note the laziness of me not including the indexing in the bottom. That's just so when we write up these proofs here that, like, the spacing gets weird in LaTeX if you, like, write that in the middle of a sentence, so I'll drop the subscripting where it's obvious where the lambdas live. Alright, and now conversely, if you're in that intersection, first of all, note, since we are empty, we can pick an element. And because we picked that element and we're in the intersection, that means we're in here, which guarantees that we're in A. So, good thing I pointed out that this set needed to be non-empty. Otherwise, I would not be able to tell you that you're actually in A. Alright. Alright, now similarly, if you were in the union, then there's some index that you belong to, but we're in this intersection, which means that we have to be in this set. So then X is not in A beta. That's contradiction. So it's got to be we can't be in the union. So we're in A and we're not in the union. So we're in that set right there. Beautiful. I like this stuff. I love working with index unions and index intersection. Like when I did my first paper, we were working with this intersection, and it was index over this weird set, and oh, this was real cool. Good stuff. So I'm a big fan of all this index manipulation. Alright. Okay, so let's return to images, but now let's talk about inverse images. So, given a function from x to y and a set A, we define the inverse image of A to be the collection of things that map to A. That's called the inverse image. The end. Right, so again, not that crazy of a thing. Worth noting notation-wise, there is occasion to do the inverse image of a set consisting of a single element, and to avoid just gross-looking notation, this gets abbreviated as follows, so we will see this pop up every so often. Alright, so, again, there are a bunch of theorems of inverse images that we can prove. We don't need to do all of them, so let's just get one in to get a flavor for it. Alright, Okay, so in particular we'll show the inverse image of a set difference is the set difference of the inverse images. So it's worth noting that the equivalent result for images does not hold. Images tend to be a little bit more not helpful with set theoretic machinery, but inverse images, everything works quite well. Alright. Which is one of the reasons why inverse images end up being like a building block to a lot of mathematics, and why they tend to pop up a bit more often. But anyways, let's go for the proof. So if you're in the inverse image of B set minus A, that means that f of x belongs to that set. So f of x is in B, and f of x is not in A. That means that x is in the inverse image of B, and x cannot be in the inverse image of A, because if it was, then f of x would be in A. So that means you're in the set difference here. Alright, and therefore we have subset in one direction, and the reverse subset is just literally read this proof backwards. Beautiful. Alright, a few more slides. Thank you for sticking with me if you're in this deep here. This video ended up being way longer than I thought it was going to be. Oh boy. Oh boy. I was actually debating doing functions as their own video, and then I was like, no, I'll just do it all in one set theory thing, and now I'm looking at how long this video's gone on for, and I'm like, maybe I should have done that. Whoops. Anyway, alright, so something that we'll do a lot of in, not just analysis, but something you do a lot in mathematics, is composing two functions. So taking a function f and taking a function g, and putting them together. Alright, so note that f takes things in x and sends them to y, and g takes things in y and sends them to z. And so f composed with f is, alright, give me things in x, and I'll spit them out in z, and this is the formula I'll do. You give me x, I give it to f then passes it off to g. Right, because x lives in x, f of x lives in y, and g takes things in y and splits them out in z. Alright. So, again, let's do a quick proof involving compositions. So we again, remind ourselves of how they work. Alright, so I'm going to prove that the inverse image of G composed with F is the same thing as doing F's inverse image of G's inverse image. Right, and this is a classic unraveling the definitions proof. Let's say X belongs to the set. That means that if I feed X into Goff over here, that lands in B, but hey, G of f of X is what that's equal to. So start peeling it off. If G of f of X lands in B, that means f of X is in G inverse of B. And if that's true, then X must be in f inverse of G inverse of B. Alright. And then the reverse subset is proven similarly. Again, it's now, right, just read the proof backwards once more. Always the best kind of proofs, where you just have to go like, just read it backwards, it's fine. I actually wrote it out here, but yeah, we're good. Alright. Let's keep going. So, a function, and here's the last couple of things we're going to talk about with functions, is said to be injective if f of x is equal to f of y implies that x is equal to y. And it is called surjective if given a y, then there exists a input that hits the output. Okay, and so, oh, hey, I have a pause missing. Alright, oh, yeah. Okay, so, like I said before with my little change of codomain rant, some mathematicians don't like that maneuver, because not every function is surjective. But you can always think of it as surjective if you change the codomain to its range, which you can do. So, some people would argue that when I talk about x squared isn't surjective because, right, there's no negative numbers that map that spit out with x squared, unless you include complex numbers. Right, but if you change its codomain to be the positive numbers, well, now it's surjective because, right, square root of x exists, so you hit every output. So, some people they get hung up on that, where they're like, well, depending on when, right, a function isn't a formula, a function's its graph. Yeah. So that's why some people kind of object to it. But again, like I said, I'm not of that opinion. All right. So it actually is worth noting that if you're injective, you can change the codomain and you remain injective, which is nice. But that's not true for surjective. If you change the codomain, you could lose surjectivity, or you can gain it. So yeah. All right. So again, let's just quickly prove a couple of things about surjectivity and injectivity. I picked ones. Again, we're not doing an exhaustive list here, but I picked ones that are useful for something that we will encounter in this course, which is invertible functions. So, all right, let's do a quick couple of proofs here. So first of all, surjective functions got the property that these inverse images are always non-empty. And a surjective and injective function has the property that these are always a single element. Alright, well, since you're surjective, that means that for any output, any element y, there's an input that hits it, so this means that f of x is in that set, so x is in the inverse image of it. Alright. Keep going. Okay, now if we throw in injectivity, we're going to verify that this only has one thing in it. Alright, point 1 ensures that this is non-empty, so pick something that lives in there. Okay, now note that this is a subset of x, so it lives in x by construction. Alright, now let's say we take any other element that lives in that set. Well, then f of z must equal y. Okay, but f of x is equal to y by the same logic, and the injectivity then guarantees that x and z are the same set. Nice. Beautiful. Alright, therefore, it's got to be that f inverse of y is this set, because the only things that are elements of it are x, so it's got to equal that set. Alright, and the uniqueness of such a thing is clear, because if this was equal to some single set, then they would have to equal each other. So, there you go. Alright, beautiful. Alright, and now, last thing to talk about. A function that's both injective and surjective is called bijective. Very exciting. The previous proposition ensures that for such mappings, for every output, for every element y, there's a unique x with this holding. That gives me access to a function, so that its output is this unique element in here. And this function then must satisfy the following. And we can show that such a function is in fact unique. It's called the inverse, and somewhat unfortunately, the symbol it gets is this, f to the -1, which is sort of indicating 1 over f, but that's not true. It's, right, this formal inverse. It's got this inverse property right here. Alright, cool. Alright, so bijections are also called invertible functions for this reason. With that concludes our brief little overview of the basics of set theory that we will frequently be using throughout the course. So, exciting. Alright. There we go. Alright. Thank you for joining me for this lengthy little introduction here, but I promise the rest of the videos will not be anywhere near as long as this one. Oh boy. Alright, that's it. I'll see you in the next one.